So I'm going to talk about the web and JavaScript and a lot of other crap. So we probably wouldn't be here if the World Wide Web were just a document retrieval system, something intended to retrieve simple hyperlinked documents. If that's all it ever became, there'd be no reason for this conference or for any of us. But it turned into an application delivery system, and then suddenly some problems occurred. The most significant one is what we call the XSS, or the cross-site scripting problem. We call it XSS instead of CSS because there is another abomination already in the browser called CSS. And I hate this name for two reasons. The first off, it suggests that there's something wrong with cross-site scripting. It turns out cross-site scripting is a highly desirable thing. It's something that came into existence because of JavaScript, and it's great. We call it mashups. It's the ability to take components from multiple parties and have them all work together cooperatively. People have been working on software components for decades. It came to life in JavaScript. It's a wonderful thing. It's not a bad thing. The other problem is that the XSS attack is not necessarily a cross-site issue at all. It can happen completely within a site. So the name completely mischaracterizes the problem. And it's a severe problem. And even though it is many, many years after the problem has been discovered, we are still calling it with the wrong name. And we're expecting developers to deal with it with the wrong name. Like a lot of things in the web, once something gets out there wrong, it's really hard to fix it. And even the basic way we think about security is wrong. So this should not be news to most of you. This is probably the simplest possible XSS attack. You trick a user into clicking on a URL which goes to your site, or where your site is the good guys, with a really weird-looking file name. And by default, most web servers will return a page in which that goofy-looking file name suddenly causes scripts to execute. And it executes in your site's domain. So suddenly that script gets access to your cookies, to your local storage, to everything that the browser entitles you to. And depending on how you validate connections to your site, or to your site, you get that too. Now you might argue, well, most users are not stupid enough to click on a URL that looks like that. And I wish that were true. But certainly there are a lot of users who will click on a URL that looks like that. And it is exactly the same level of danger, or perhaps even greater danger, because there's no way anyone could anticipate what it's going to do. And we're clicking on this crap all the time. So everybody should know what happens if an attacker can get some script into your site. But here's what happens. An attacker can request additional scripts from any server in the world. The browser has the same origin policy, but it does not apply to script loading. So he can go to the evil site on the planet and download as much script as he needs to continue his attack. The attacker can make requests of your server, and your server cannot detect that the request did not originate with your application. Now, if you're using SSL, and you should, the user gets access to your SSL connection. If you have crumbs or other tokens of authentication, and you should, the attacker has access to all of that as well. The attacker can read the document. He can see everything the user can see and things the user can't see, like hidden fields, comments, cookies, local storage, everything that is available in the browser, the attacker gets it. And the attacker has control over the display and can request information from your user. And the user cannot detect that the requests did not originate with your site. A lot of the browsers now have anti-phish in Chrome. Unfortunately, most users don't pay any attention to that. But if they did, in this case, it will tell them, go ahead, give it up, because this is a legitimate site. Because all the browser is looking for is where did the HTML come from. It is not at all concerned with where did the script come from and whose interest does it represent. Some sites, knowing this, will, whenever the user does something that's potentially dangerous, ask for a password, assuming that only the user will know that. But the attacker has control over the display, so the attacker can ask the user, what's your password? And the user will probably give it up because everything says it's okay. If you have a site which routinely asks the user for passwords at unexpected times, then you are conditioning your users to give it up as soon as the attacker asks for it, and they will not think that anything is wrong when that happens. The attacker can then send the information that it has gotten from your server, from the browser, from talking to the user, and send it to any server on the planet. Again, the same origin policy prohibits the ability to read harmless data from other sites, but does not prohibit you from sending that data to the worst sites in the world. The consequences of an attack are horrible. There can be harm to customers, loss of trust, legal liabilities, potential criminal liabilities. So this is really, really bad. And this is not a bug. Now, obviously, browsers are full of bugs. Every browser is as buggy as a Texas anthill. Yeah. And bugs certainly cause security vulnerabilities, but I'm not talking about bugs. This is standard behavior. A browser that does not expose sites and users to this risk is not standards compliant. That is the state of web standards. So why does this happen? For a number of reasons. First, the web stack is way too complicated. We have way too many languages, HTTP, HTML, CSS, JavaScript, URLs, SQL, and more, each with its own encoding, quoting, commenting, and escapement conventions. Had we thought of this thing as a system, we would have had one convention, for example, for strings. So everything would be double quoted with backslashes, and that's it, everywhere, end of story. But instead, we've got entities and things with % signs and all sorts of stupid stuff. And coming up with encoding schemes which work for all of those in all contexts turns out to be really complicated. And when you put that much complexity in front of developers, things go wrong invariably. And we can feel good about blaming the developers for not being diligent enough, but really it's a systemic problem. Then each of these languages can be nested inside of other languages, which makes it even harder. And then during the 90s, there was this insane competition between two browser makers to try to make sense out of the worst possible markup that was being developed by horribly incompetent webmasters, with the idea that if you could make sense out of more crap than the other guy could, then you get more market share. And those rules are now baked into standards. Then on the server side, we have template-based web frameworks, which were optimized for XSS injection, including PHP, ASP, JSP, all those Ps, make it possible to correctly encode stuff, but the default is to do it wrong. And so very often it gets done wrong. So then you have that big pile of oily rags. JavaScript then is the lit match that's tossed into that. The JavaScript global object gives every scrap of script the same set of powerful capabilities. And that's why XSS happens. So cross-site scripting attacks were invented in 1995. They came into the world with Netscape Navigator 2. Netscape Navigator is long gone. Netscape is long gone, but the SSS attack is still alive and doing very, very well. We have made very little progress in solving this problem since then. We have made some baby steps, I'm happy to report. So we have the content security policy, which is still in draft, which makes it possible for a page to talk about where script can be inserted and what capabilities it might get in a limited way. That's certainly a step forward. We have the sandboxed iframe. I proposed this at the Open Ajax Alliance in New York in 2006. It's such an obviously good idea. I'm sure lots of other people proposed the same thing, perhaps even earlier. And it's gratifying that 6 years later, it's in a working draft. So these are both good. These are necessary Band-Aids, and it's good that we have them. But the browser is still unsafe by default. You have to use these and know to use them. The default behavior of the browser is to not use these, and so the danger continues. Now, as bad as the browser is, it is better than everything else. There have been lots of application delivery systems, many designed and developed after the web. The browser is still the best of all of those. Everybody gets serious stuff wrong. Everybody refuses to learn the lessons of the browser. The principal mistake they make is, we'll add security later. You know, the hard part is getting the system to cycle, it's getting the boxes to talk, it's getting the pixels to light up. Once we figure out how to do that, then we'll think about how we're going to secure it. And that turns out to be wrong. Security needs to be the first consideration, not the last consideration. So JavaScript gets beat up a lot for its security problems, but JavaScript actually got close to getting it right. It can be repaired by subsetting, becoming an object capability language. And once it becomes that language, we now have a platform in which we can start thinking about how to develop secure applications. There are other languages which can't do that. You know, Java, for example, got some early fame as being a secure language, was never able to demonstrate it. Client-side Java now, its principal role is as an attack vector. It isn't used for application delivery anymore. It didn't work. So, but JavaScript can become a secure language not by adding more crap to it, but by removing some of the crap that it has from it. So what's very good and what's very bad about JavaScript? On the very bad side is its dependence on global variables. JavaScript doesn't have any kind of a linker, so it throws all scripts into a common global space where they all get to duke it out for control of the global variables. That turns out to be really bad for reliability. It's even worse for security because it means every script gets access to the global environment, which includes the DOM and all of the other capabilities that are necessary for an XSS attack. A bigger problem is ignorance. Most of the people who are writing in JavaScript literally do not know what they're doing. We have a lot of people who come at it from the web side who have never had any formal training in programming, who learn JavaScript mostly from horrible websites or from doing view source of really horrible applications, most of which dates back to Dreamweaver. Really awful stuff, and it keeps propagating. But we see it on the professional side too. We see a lot of programmers used to be doing .NET and Java moving into JavaScript because that's where the jobs are. And they keep hold of their ignorance of the language. And it's like, okay, I'd rather be working in a man's language. Okay, I'll write your JavaScript. But there's no way I'm going to know what I'm doing. It's principle. JavaScript is the only language that people feel good about not knowing what they're doing. You don't see that mistake made in any other language. And JavaScript also suffers from some major design defects. I think Brendan Ike's going to be here tomorrow. He might talk about a couple of those. He had 10 days to design and implement the language, which is an insanely short amount of time. Netscape was a seriously mismanaged company, and they took given the way that company was managed and the resources they gave him, it's amazing that JavaScript is as brilliantly good as it is. But it's easy to not get everything right when you have that deficit of time, and that's what he had. So there are major things in the language which definitely impair its security, some of which can be repaired, some of which can't, and we'll talk about some of those later. In the very good column, it has functions as first-class objects with lexical scoping and closure, which is the best idea in the history of programming languages. We first saw it in Scheme at MIT in the early 70s. It was mostly rejected by the mainstream because they couldn't get past the parentheses. JavaScript was the first mainstream language to have this and to get it right. And now virtually all languages have it. It has become a popular feature. JavaScript became an influential language because it brought this idea forward, and it's brilliant and wonderful, and we can actually use that to build secure systems. About the last language that doesn't have it is Java. Java's having a really tough time keeping up with its stupid little brother. JavaScript has prototypes, which was based on the self language, which is the next step in the evolution of object-oriented systems. It turns out that eliminating classes makes the language more powerful and more expressive. It's not a regression, it's the step forward, but most of the industry has not discovered that yet. And simplicity turns out to be a huge beneficial feature, especially when you're looking at secure systems. The simpler a thing is to reason about, the more likely it is we're going to reason correctly. And JavaScript benefits significantly from being a simple platform. Now, the problem we have in the XSS problem is the confusion of interest. Now, it turns out that the browser does this better than all of the other application platforms, which mostly started with the idea that a program represents the user's interest. This is something that was certainly part of Unix. Unix assumed that a user was a programmer and whatever programs the user ran represented the programmer. That turns out to be really bad. The browser is smarter about that. It assumes that the program represents the site and not the user. And so it will distinguish between the interests of those two. And that turns out to be a huge benefit, a huge step forward, something that everybody has continued to get wrong after that. The thing the browser did not anticipate is that there might be multiple interests on the page. It assumed that all of the script came from one party. And we know that's not true. We have scripts coming from lots of different parties, all mingling, all wanting to work cooperatively for the benefit of the user. But because of that confusion, all of those scripts are assumed to represent the site. And that's the origin of the cross-site scripting problem. So within a page, interests are confused. And if code is on the page intentionally, not accidentally as in the traditional XSS attack, the same problems happen. So an ad or a widget or an AJAX library, they all get the same rights as the site's own script. So your metrics, your ads, everything can do all of the things that I talked about earlier in the attack scenario. They can all do that. So the level of trust you have to have is extraordinary. Knowing the damage they can cause, why would you ever put anybody else's code on your page? So one of the reasons we still have a web, I think, is because we figured out mashups. Mashups are extremely important. But a mashup is a self-inflicted cross-site scripting attack. It's where you're taking third-party code and intentionally putting it into a page, hoping that it's not going to misbehave. Turns out advertising is a mashup. So the most reliable, cost-effective way of injecting evil code now is to buy an ad. That's the most straightforward way of accomplishing this now. So I developed a system called ADsafe in 2007 in order to make it possible to take dynamic ad scripts and put them onto a page and be confident that that script cannot do any of the evil things that we've talked about. And you can read more about AdSafe at adsafe.org. So AdSafe defines a safe subset of JavaScript. It identifies a number of features about JavaScript which are either known to be problematic or difficult to reason about and says, okay, you don't get those. But it leaves enough of a language there that you can write interesting stuff. JavaScript, or AdSafe does its work by static validation only. It doesn't do code rewriting as Google's Kaha or other safe JavaScript platforms do. So as a result of that, there's no impact on performance. It doesn't have to add indirection or runtime checking in order to make sure that the script is not going to get out of hand. It can do it all statically. And because it does that, the code that runs is the same code as the code that was submitted. AdSafe's validation is not destructive, so it can be performed at any and every step in the ad delivery pipeline, from the creation of the creative to its handling at the agency, to delivery to the ad network, ultimately to the publisher, and can even be done post-user in order to test compliance. So if AdSafe determines that there's a problem at any step in the pipeline, we can kill the ad at that point. So the multiple points of validation provide greater confidence that bad content will be blocked. So these are some of the rules that AdSafe provides. One of the problems with AdSafe is that the percentage of existing programs which will pass the AdSafe rules is 0%. They are very strict rules, much stricter than you'd see in any web application. And so applications have to be written specifically for AdSafe. But the rules permit the development of good programs. So there can be no global variables or functions because global variables are evil and we're not being tolerant of evil. The only global variable you can access is the AdSafe object, which becomes the conduit by which capabilities are delivered to the widget. Names starting or ending with underbar are not allowed because these are often used to indicate privacy in other applications. And there are a number of words which cannot be used as variables or property names. The most hurtful one of these is this. This is the thing that's used in object-oriented programming for associating a method with an object. Unfortunately, there's a horrible design error in JavaScript which will sometimes bind this to the global object, which is exactly the thing we want to prevent. So the ADsafe rules say you cannot be writing with this. So that makes object-oriented programming really difficult. But fortunately, JavaScript is also a functional programming language, and all of the functional programming facilities are unimpaired by this. And so it's still possible to write good programs, but it's a different style than most people are used to. And the other heartbreaking thing is that use of the subscript operator is restricted because we can't know what properties you're going to be going after. So unless ADsafe can verify that the value is going to be a number, then bracket is not allowed and you have to use get and set methods instead. So ADsafe will accept a template which can be inserted into a web page with confidence that it's not going to be able to break its containment. So in the template you can specify some HTML content, and you can even give names to or IDs to the fields within that HTML content. And then you can have some script which will be given an API which allows it to do querying on that local piece of DOM so that it can manipulate the nodes that it has. So ADsafe cannot allow scripts to have direct access to the DOM because all DOM nodes are linked together. So if you can get any DOM node, you can trace them all back to the root, and the root gives you access to the entire document and to the network, and we don't want to do that. So everything has to be encapsulated in a DOM API. So the API provided by ADsafe is lightweight, it's query-oriented. The scope of the queries is strictly limited to the widget's div. You cannot query outside of the div, so you can't look at what else is in the document. And the guest code does not get direct access to any DOM node because it's dangerous. So the guest code is not allowed direct access to DOM elements, access to any element because of all the stuff I told you. Also document.write, which is one of the stupidest ideas we've ever seen anywhere. It's terrible. But it's widely used in ad networks. It's very common for an ad placement to run a little script which will do a document.write, which will bring in another script, which will do another document.write, which will bring in another script, which will bring in another document.write, which will get a script, which will finally deliver the ad. They're really terrible practices in the advertising industry. So ADsafe is implemented as an option on JSLint. JSLint is the JavaScript code quality tool. If you're not using JSLint, there's something seriously wrong with you and your code. It defines a safe HTML and JavaScript subset, and it will reject all JavaScript features that are unsafe or suspect. And it allows ads and widgets to safely interact for the benefit of the user, presumably. And because it's implemented in JSLint, you also get much better code than you would get otherwise, because it turns out there are lots of coding practices that are possible in JavaScript which are dangerous not from a security perspective, but from a reliability and readability, maintainability perspective. JSLint will insist that you clean that stuff up as well. Some of the worst code you've ever seen is the stuff that's delivered in advertising. It's horrendous. So ADsafe works, it's really effective, but because it's running in the browser and because of the inherent problems in the browser, there's still dangers. ADsafe protects us from all known browser defects, but there are almost certainly defects out there that we do not know about yet or which have not occurred yet. For example, there was something that was in Firefox almost from the beginning, or perhaps even before the beginning, where if you tried to take the -6 element of a function or some other structures, you would get stuff that was unexpected. It was added to the Firefox JavaScript engine maybe as a convenience, but was completely undocumented and unknown until someday somebody was reading the source and said, wow, I didn't know you could do that, and published it. Look at the neat thing you can do. And it turned out you couldn't do anything that you couldn't do before, but it was now possible to get stuff through all the safe JavaScript subsets because none of us knew about this. So on that day, all of the safe JavaScript subsets were broken. We alerted Mozilla about this, and they very quickly fixed it. And a year later, all the browsers were updated, and then we didn't have to worry about it anymore. But for a time, AdSafe could not allow any use of the bracket operator because there were, the guarantee that it was going to be a number wasn't good enough, because if it was a negative number, it was going to cause problems. In the ECMAScript standard, there's a Chapter 16, and Chapter 16 gives license to makers of JavaScript engines to basically do whatever they want. They have a very broad license for adding new features to the language, which is good in terms of experimentation and helping us to get experience with improving and evolving the language, but it's very bad because browser makers are, by the standard, entitled to make changes which can break AdSafe and other safe JavaScript systems. So that's a problem going forward. Then finally, the last danger is something that's inherent to JavaScript itself, that there are a number of things in JavaScript which are maybe unnecessary, but simply by their existence in the language make secure programming unnecessarily more difficult. I'm going to show you some examples of this. So here's a problem. If you have a piece of paper or a laptop, you might want to try to solve this right now. Given an array of whitelisted names, make a set function that takes a string and a value and sets them on a secured object. So here I've got a set maker, and I'm going to pass it an array of strings, in this case just one word, status, and it's going to return a set function, and then I'll call the set function, and if I pass it status, it will work, and if I pass it bad, it should fail. Okay, everybody clear on the assignment? Okay, go. Okay, so here's the solution. We've got our set maker, which takes a whitelist array. It's going to make the object, and the object is going to be within its closure, so nobody can get directly to the object. So that gives us a great level of security. And we're going to return our set function, which will take a string and a value, and we'll search for this string on our whitelist. And if we find it, then we will allow the setting to occur, and otherwise we'll throw. Anybody see the obvious problem with this code? Anybody? Well, here it is. It turns out JavaScript not only has strings, it has objects which can pretend to be strings. An object which has a value of method can act as a string. So in this case, we have an object which will toggle between two strings. So each time you look at it, it might appear to be one string or the other. Now, this boxing of string types in JavaScript is completely unnecessary. It's something Brendan borrowed from Java because Java does boxing all over the place, and he thought it might be useful. Turned out well, it might actually be useful, but it's more confusing and dangerous. And so it turns out in code like this, you have to explicitly ask, are you really a string? That simply having it return a value which is a string and acts like a string is not sufficient. That's really, really bad, and we cannot remove this from the language. So this is a hazard to people who are trying to write secure code in this silly language. Okay, here's another one. Make an array wrapper object, or actually I guess we're making a vector object, with methods get, store, and append such that an attacker cannot get access to a private array. Okay, so we'll make a vector, we'll append to it, we'll store to it, and stuff like that. Okay, so and here's the answer. Now, it turns out that an attacker, simply by using the three methods that are provided here, can get direct access to the array, which is something that we're trying to keep controlled. Okay, so we can't have confidence that we can have contracts which are valid when confronted with third parties. And so here's the attack. I can store a value called push and have it be my own function. And that function will get called whenever you call the append method, and that gets me control. Now, this attack works because JavaScript doesn't really have arrays. It has objects which act like arrays. And most of the time that's okay, it works, but there's this confusion, and confusion generally favors the enemy. In this case, the confusion is that they aren't really arrays, that they're really objects, and that like any object, you can have members which have ordinary names, which happen to replace methods that appear to be built into the thing. So in my opinion, push should have been a primitive operation, not a method. Had it been an operator, then this sort of attack couldn't occur. So because the attack can occur, you have to write this a little differently. You can use a different idiom for writing the append, just because, as we've seen, push is problematic. Or we can use the plus prefix operator to guarantee that the values that are passed into get and store are actually numbers, because plus is the type coercion operator to number. If I do any of these things, then I now have a secure function. Okay, here's the last one. Make a function that makes a publish subscribe object. It should reliably deliver all publications to all subscribers in the right order. Okay, so I'm going to make a pub sub. If I call it subscribe method, giving it alert, and then I publish something, then the alert should fire. Okay, everybody clear on the assignment? Okay, so here's how you could implement it. Again, we've got our subscriber arrays in a closure, so it's a safe thing, and we're going to return an object containing a subscribe method and a publish method. It turns out there are many attacks that I can make against this code, which will cause it to violate the contract that I talked about earlier. So here's the first one. I can simply replace either of those methods with my own method, which will hijack it or do something different. So doing that, it means it's not safe to share my pub sub object with third-party code because they can interfere with it. In ES5, in the 5th edition, we added object.freeze, which takes a object and makes it immutable. And that corrects this problem. So now I can give this immutable object anybody and nobody can change it. All they can do is call its methods. The underlying data behind it, the subscriber array, is still immutable. It's just the object which is its interface now is not. And that turns out to be a really good thing. So ES5 takes us a long way toward becoming a secure system. Here's another attack. I can have my subscribe function throw or fail in some other way, which means that the other subscribe functions after me don't get a chance to run. So I could fix that by putting a try catch in there. Okay, here's another attack. It turns out that the subscribe functions accidentally get access to the subscribe array because in JavaScript, this gets bound to the object that functions are coming from. And so in this case, the subscribers array will be mapped to this. And once they get that, they can delete stuff, they can move people around, they can steal them and call them inappropriately, they can do all sorts of stuff. And this is another one of those things about the language which is unnecessarily confusing, that you wouldn't expect things being called from an array to have that binding, but they do. So we can fix that by using another new ES5 feature, array for each, which will iterate through the elements of an array and completely avoid that problem. So the code actually gets nicer with that fix, so that's good. And there's one other. If I have a subscriber publish as a result of his subscription behavior, then he can cause messages to be out of order because the new messages will be delivered to the people after him before the old message was. So we can solve this by using set timeout or set immediate to schedule each of those subscriber callback functions to happen in a later turn. JavaScript is generally a turn-based system. And by doing that, it's no longer necessary to do the try-catch, so that's a little bit nicer too. So one of the requirements about working in this environment, especially if you're working in Node.js or some other server environment, is you have to respect the law of turns. And it turns out that's easily done. You just need the education. We've been doing some work on a new dialect of JavaScript called secure ECMAScript. And at one time, I thought we were going to have to fork the language in order to accomplish this. But it turned out that's not going to be necessary as a result of some of the work that we did in ES5, the fifth edition. The fifth edition was very much informed by the work that I did on AdSafe and the work that Google did in Kaha and work that was done at Facebook on FBJS and other work. So that got factored into the fifth edition. The most obvious feature of this was use strict, which is a pragma which can be added to any script or any function, which repairs some of the worst things in the language, including the binding of this to the global object. That no longer happens. So as a result of that, and some of the other things we were able to do, we can now allow for an AdSafe-like static verifier on third-party code, except allowing for use of almost the entire language, not restricting use of brackets or this. So that we can allow much more third-party code to be running in a safe mode, provided that our code is guaranteed to run before anybody else's code. If we can run some code first, we can do things like remove or hiding some of the primordial objects, things which grant too much capability by default. We can freeze objects to prevent the third-party code from modifying them or mutating them or turning them into something that's going to compromise other code. And if we can do that, we can actually start to approach a secure environment, which is an amazing thing. But there's still more to do. While we can protect the page from the widget, we cannot protect the widget from the page. And there's some applications which really need that bidirectional security, and we cannot provide that in the current language or the current browser. So the corpus of known hazards is vast. I mean, basically, you're all here to talk about, hey, guess what I just found, and celebrate the discovery of it. But there is way too much stuff for anybody to know and understand, and it's constantly growing, and while some of it expires very slowly. And so as a result, there is much more to know about the security of the browsers than any developer should ever be expected to know. So as a result, we continue to see a lot of bad code being developed, even when it's the intention of the developers to write good stuff, because there's still too much complexity in the platform, or because they're mismanaged. And we're seeing even more developers who don't have that ambition, and so they're just writing bad stuff, not knowing that they're writing bad stuff. And it'd be good to fix this, but it's hard. We're seeing, in the web standards that we are adding complexity at a much faster rate than we're adding Band-Aids. And we're not fixing much of the fundamental stuff. I mean, JavaScript, we were able to add the use strict pragma, so we fixed this and a couple other things. But I don't think we're going to get to do that again. The 6th edition will probably not repair any of the breakage. It will just add a lot more stuff. And so the language is going to get much more complex. It's not going to get more secure, and that's going to be a problem. And we see a similar thing in the web. Once something gets into the web, it's really hard to get it out. So there are some exceptions. For example, we got rid of the blink tag. Yay. But not much else. Pretty much everything else is still, Yeah. So there's a lot to do, and I would really like to end this on a positive note. I really would. But most of all, Sammy is my hero. Thank you and good night.